In this video, we're going to talk about quantitative reasoning strategies with decimal accuracy. We will still use the 7 steps to identify and solve an application question, but we do want to talk about the uniqueness of accuracy. Unless otherwise stated, accuracy is assumed to be rounded to the same number of decimals as the value given, with the least number of decimals. Another way to say that is you can only be as accurate as the least accurate measurement. So let's talk about what that means. In example 1 for a biology experiment, a mother decided to take height measurements of her 12-month-old each month for 6 months and mark the growth increments on a wall with a pen. At the end, the following increments were documented in centimeters. So the lengths of growth or the increase each month was 1.21, 1.16, 1.09, 1.118, 1.1, and 1.0. And this is in centimeters. What was the total growth in 6 months? If each one of those lengths represents an increase in height of the child over the 6 month period, we can add them all up. Notice that I'm being careful to keep my decimals all lined up and my place values all lined up. So I've rewritten all the values, and now I'm going to add them up from right to left, carrying the tens as I go. So 8 just drops down. We have 10, 16, 17, carry the 1, 3, 4, 5, 6. Now the decimal place, and now I'll count out these 1, 2, 3, 4, 5, 6. So we have 6.678 centimeters. But what was the total growth in 6 months? For accuracy purposes, the smallest or least accurate value would be these two right here, 1.1 and 1.0, because they were only accurate to the tenths of a centimeter. Therefore, we have to round to the tenths place. And just a quick refresher on rounding, if the number after the decimal place we have to round to is 5 or more, we round up the 6. So since 7 is 5 or greater, we add 1 to the 6. If it was less than 5 in that second decimal place, we would just stop at 6.6 and not change it. We wouldn't subtract from it. That would be wrong. So our final answer is 6.7 centimeters. This is an accurate measurement or accurate sum because our least accurate value is 1 decimal place. If we were to write this as an equation, we could assign total growth to be G, and we could say that the sum of the lengths equal the total growth. So we could write it as 1.21 plus 1.16 plus 1.09 plus 1.118 plus 1.1 plus 1.0 equals G. Now, we would still need to round for accuracy purposes, but this is how we could solve it. So we could say that 6.7 centimeters equals G, the growth of the child. In example 2, a student gained 15.75 pounds during their freshman year in college, but started working out in the gym and lost 13.2 pounds. How much does a student weigh now if they started off weighing 149? Let's go ahead and list their original weight, 149, and let's add 15.75 to that weight. So now we'd combine these, so we'd have 0.75, adding 5 and 9 together, we'd get 14, carry the 1, that would give me 6. So their weight after they gained 15.75 pounds is 164.75 pounds. But then they go to the gym and they lost 13.2 pounds. So now we subtract 13.2. This gives me 0.55. To the right of the decimal, 4 minus 3 is 1, 6 minus 1 is 5, so 151.55. Now, because our least accurate value was 149 pounds, we can't assume that we can be accurate to hundredths of a pound, because maybe some scales are showing accuracy to hundredths of a pound, and some are just giving whole number weights. So we're going to only take the whole number weights. So if we look at the value to the right of the decimal place, we have a 5, and so we would round this up to 152. That's as accurate as we can be. If we were to write this as an equation to solve, again, we would need to find the weight now for the student. So we could call that W. We could also write this as an actual equation and say 149 plus 15.75 minus 13.2 is equal to W, the weight now. If we combined these, we would still need to use the accuracy method of rounding, and we would still get 152 as our final weight, but we could say that's equal to W.